So the portion on boiling heat transfer has been completed. In that we talked about pool boiling, the boiling curve, then the correlations, different boiling regimes, correlations particularly for the nucleate boiling regime, and one numerical, salt numerical in the book was talked about. And then the flow boiling, the different regimes in flow boiling were discussed. Now let's start talking about the condensation heat transfer phenomena. So obviously condensation would occur. When we are talking about condensation, uh, we are talking about the condensation of vapor, right? We are talking about condensation of vapor, and the condensation of vapor can occur if it is exposed to temperatures less than the saturation temperature of that vapor at given pressure. Okay. So if you have, let's say, the pressure is atmospheric pressure, and uh, the water vapor exists, maybe slightly superheated, or at 100, or let's say 101 degrees Celsius or something, and there is a plate which is at a temperature lower than 100 degrees Celsius, right? There has to be a temperature difference. In case of boiling also, we talked about delta T excess, that is the temperature of the solid surface has to be higher than the temperature of saturation temperature of the fluid. Then the conversion from liquid phase to vapor phase starts or can occur. Here it is the opposite phenomena, that is vapor is saturated or superheated, and the solid surface is at a temperature lower than the saturation temperature. Then the condensation can occur. Here we will be talking about only the condensation of vapor occurring on a solid surface, but it's not that condensation can occur in only that mode. It can occur inside a gas also, like the rain coming from the clouds, right, which is a very complicated phenomena. But here we'll, as I told, we'll be talking about the condensation which an engineer comes across in many industrial phenomena, or in different types of, even in different types of heat exchangers. For example, a heat pipe, or you are talking about condensation occurring in a condenser of a refrigerator, right? So here we are talking about condensation of vapor on a solid surface. So those kind of phenomena is depicted in the diagram shown on the left hand side. Now there you see two different diagrams. The plate surface temperature is shown 80 degrees Celsius, and on the left hand side you can read film condensation, and the right hand side diagram, it's written drop wise condensation. So in this right hand side diagram, you see something like dew formation, which is many times seen in nature. But the left hand side is film condensation, and it is seen that this is more common phenomena, particularly for human made systems. The condensation occurring on a solid surface, and that liquid clinging to the surface of on which this condensation is occurring, and then it is making a film, and because of gravity it continuously slides down. So as you see on a vertical plate, the thickness of the liquid film will go on increasing as you go down. Okay, and then finally at the end of the plate it is going to fall down. So what you see on the right hand side diagram is called drop wise condensation, and it is seen that dropwise condensation is much more effective way for heat transfer, though condensation itself, like boiling, is a very effective heat transfer phenomenon. You get reasonably good or quite good heat transfer coefficients. But if it is dropwise condensation, it can give you even more higher heat transfer coefficients. The reason is that when there is a liquid film on the surface, it creates a additional resistance to the heat transfer between the vapor and this cold plate, right? And because of that, the heat transfer coefficients are low. But in dropwise condensation, it is much higher, and it is sometimes even 10 times that of what you see in film condensation. But it is seen that dropwise condensation is not sustained, and it gets converted into film condensation. And in order to achieve dropwise condensation, sometimes the surfaces are also treated, some coating is made so that the adhesion is not good. But it is seen that over a period of time, many times that surface loses that property, and finally the film condensation starts occurring on that surface. So to be conservative, you may assume that the condensation which is occurring is film wise condensation, because sometimes you may not have access, or you may not be able to see what exactly is happening inside a particular device. So most of the times it is analyzed as being film condensation. So there is a difference between film condensation and dropwise condensation, but more commonly the film-wise condensation is assumed, and analysis or the correlations for that type of condensation are used while finding out the heat transfer coefficients. So again, now the diagram on the left hand side, you see the film condensation phenomena explained on a vertical plate. So the left hand side gray plate is a vertical plate whose temperature should be less than the saturation temperature of the vapor. So here you have the vapor. Right now here you are assuming that the vapor is not having any like a bulk velocity. Okay, so it's almost kind of stagnant. Though microscopic movement do occur, but macroscopically there is no bulk movement which is shown. So if the vapors do not have very high velocities, you may assume this kind of state. So vapor V, and then this film is going to move down because of gravity, right? So that gravitational acceleration has been shown, and here you can see the x direction and y direction, right? It is opposite of what we used to show for flow over a flat plate in case of external flow forced convection. So conventionally, like x is taken on in the vertical direction for a vertical plate, and y is your horizontal direction, and this is the origin O and the cold plate. So this surface, the condensation is occurring only on one side, because let's say vapor is existing only on one side of this cold plate, and you may be you have to take away the heat continuously from this plate, otherwise it cannot remain at that temperature or at a temperature less than the saturation temperature of vapor, because there is a heat transfer from vapor to the plate. Okay, so you are basically cooling the vapor. Okay. So now if you are talking about the top of the plate, then the thickness of the film condensate, you can call it condensate, the liquid which is formed by condensation is condensate. So that condensate, the thickness of the film is starts from 0, and it is continuously increasing, because whatever liquid is formed in the top portion is moving down and there is some fresh liquid also added to it. So the thickness goes on increasing. So there is some mass flow rate of the condensate flowing in the downward direction. So all these things are schematically shown in the diagram. So whenever you draw a diagram to explain some phenomena, one should show all important information in the and many times, like, you did not write a long text inside this. You can also show it in a particular way, the way it is shown here, m dot suffix x. So basically what you are showing is there is mass flow of the liquid occurring in the downward direction in x direction. Okay, so then this is liquid vapor interface. So this gray region is all vapor, and this is liquid vapor interface. Then the temperature profile is shown. So here the temperature is TV infinity, right? So this is the temperature of the vapor at enough distance from the plate where there is no temperature, there is no effect of the lower temperature of the plate. So that's the temperature in the free stream, you can say. So it may be even superheated, the vapor may be superheated, and here the plate is at a temperature less than the saturation temperature, and it starts from that temperature and it is continuously increasing as you move away from the plate, and you may come across the saturation temperature somewhere, and it may be even, like, because of the interaction with the vapor near the interface, the temperature of condensate may be even slightly higher than the saturation temperature, while it is the opposite thing here, that the liquid is a bit subcooled, goes to a temperature less than the uh, saturation temperature of the vapor. Then the velocity profile is shown. This profile is bit different from that of the flow over a flat plate, where we took generally horizontal plate. So there the velocity continuously goes on increasing as you move away from the plate. But here what is happening is we have assumed that this vapor is not having any net velocity. So it has to be zero here and it has to be zero at the plate also because of no slip condition. And as you move away from the plate, the film is continuously moving down. So the velocity is there, it's increasing as you move away from the plate, reaches some peak value, and then again it has to decrease and finally become zero inside the vapor region. And in some area there is effect of the liquid velocity, so there can be some like drag of the vapor, as well as here there is some, because of the like vapor being stagnant, the velocity is bit lower at the interface. Okay, so here the condensation phenomena occurring over a vertical flat plate is explained schematically. So in case you have to explain this phenomena, right, your diagram is the most important diagram which conveys most of the ideas, and then little text may be added to explain the phenomena. So this is a very classical example. Generally the study of film condensation will start with this type of case, the condensation occurring over a vertical flat plate. And then you can have the analysis of this type of problem, and some correlation may be developed for getting the heat transfer coefficient. Before going to that, we have to see how you can get the Reynolds number. So Reynolds number, the definition is rho Vd upon mu. Okay, so the diameter has to be the hydraulic diameter. Rho is that of the liquid, right? Because this film is all liquid. The condensate film is all liquid, so it has to be liquid density, and then the velocity of the liquid film which is moving down, and then the viscosity of the liquid. So the hydraulic diameter, the definition is 4 into cross-sectional area upon P, the wetted perimeter. Right, the word wetted is very important. Wetted perimeter. So you when you are finding or writing or replacing the value of perimeter, you have to see what how much length is wetted, and then this rho and V. So this AC rho AV, right, is actually the mass flow rate. So you may write it 4 into mass flow rate upon perimeter into the viscosity, dynamic viscosity of the liquid, or how much will be 4 AC upon P. So you will be able to get it, see that its value is equal to 4 delta, right? Its value is equal to 4 delta. So basically hydraulic diameter is equal to 4 delta. So a diagram will be shown where you will be able to understand how it is 4 into delta. Delta is the thickness of the condensate film. So here hydraulic diameter and then the perimeter cross-sectional area would be equal to perimeter into this delta. You will understand that with the help of the diagram. Next it is coming. And the other parameters which are already known to you. And the latent heat of vaporization is going to play an important role because that is what is lost by the vapor. Mainly that is what is lost by vapor. But of course, there is some subcooling also occurring. CP of the liquid also is playing some role, and there is also some cooling of vapor from superheated state to saturation, right? So there is some desuperheating also. So when you write the heat transfer rate, you may have to correct the value of HFG, and different ways of correcting it has been proposed by different researchers. We'll see about that later. But now this diagram explains you how hydraulic diameter is equal to 4 delta. Let's say you're talking about this vertical plate, right? And the depth of the plate is say L. It's not the height, it is what you see perpendicular to the page in a 2D diagram. So that is taken as L. So how much is the wetted perimeter? Now perimeter, if you talk about perimeter, you may feel that this is 2L plus 2 delta, right? But what is wetted? Wetted is only this L, length L, that of the solid, right? So that wetted perimeter is only L, and then cross-sectional area is L into delta, right? This plane, the bottom plane. So that is delta into L. That is the cross-sectional area at a given height of the plate. So hydraulic diameter is 4 AC upon P, so which is equal to 4 delta. And it is also 4 delta for other geometries like vertical cylinder, because condensation may be occurring on a cylindrical surface, on the surface of a vertical tube, or on the surface of a horizontal tube. For example, in a condenser of a refrigeration system, if you are using a shell and tube type of condenser, and let's say you're using water for cooling of the refrigerant. So refrigerant is condensing over the surface of the tube through which the water is flowing, or even in your steam power plant, the condenser. So steam condenses over the surface of the tube, right? So that is also a very common phenomena which is seen in different industrial applications. So here the perimeter is pi d, right? This perimeter, wetted perimeter is pi d, and cross-sectional area is pi d into delta. So again, this hydraulic diameter would come out to be 4 delta. Similar thing for a horizontal cylinder also. Perimeter is 2L. So 1L here, the length of the cylinder, horizontal cylinder, 1L here, and another L on the other side. So, and cross-sectional area is L into delta on one side, and there are two such sides, so 2L delta, and hydraulic diameter 4 AC upon P, so that is also 4 delta. So all three geometries, the hydraulic diameter is 4 delta. And what I was talking about, the modified latent heat of vaporization, because when condensation occurs, there is some subcooling also. So in 1956, which worked did some pioneer work on the finding the this heat transfer coefficient in case of condensation. So he proposed this HFG, modified HFG, HFG star equal to HFG plus 0.68 CP of liquid, and that should be an average CP for like if your saturation temperature is 100 and you kept your plate at 80, so this difference multiplied by the CP at average temperature, that is 80 and 100, so 90 should be found at 90 degrees Celsius, right? And this 0.68 is based on the experience or experiments. Okay, but then there could be some desuperheating of the vapor also. Vapor may not be at saturated temperature, saturation temperature. So in that case, you may write this modified latent heat of condensation equal to HFG plus 0.68 CPL. This part for subcooling of the liquid, and this part is for desuperheating of vapor. So vapor may be at 110 degrees Celsius, but saturation is 100. And then you find the CP of vapor at 105 degree Celsius and put it here. So that's how you get the modified this HFG, right? So the rate of condensation M into HFG would give you the rate of heat, total heat transfer rate because of this condensation phenomena, which should also be equal to heat transfer coefficient into the surface area uh, available for the heat transfer in this condensation heat transfer phenomena, and the temperature difference which is responsible for the heat transfer phenomena, right? Okay. So here AS is the surface area for heat transfer, and then if you solve for m dot, so if you put the values from the previous equations, you can get this Reynolds number equal to, basically m dot is replaced from here, right? So you can put it here. So you get 4 q dot upon p, that is perimeter, mu l HFG star modified one. And then you may also put q dot equal to this. So in that case, you get another expression for Reynolds number. So these expressions are useful if you already know q dot and you want to find out the Reynolds number, or you know some other parameter and you want to find out Reynolds number. So other expressions for Reynolds number, which may be useful in different cases. Now talking about the flow regimes, and the properties are generally found at the mean film temperature as it is shown here. Okay, now talking about the flow regimes, at the top, like in case of external flow, Reynolds number is equal to 0. And as it moves down, the velocity and Reynolds number goes on increasing. And at some point you reach Reynolds number equal to 30. Now beyond that, it is seen that before Reynolds number equal to 30, it was smooth and wave free. But beyond 30, it is found that there are some ripples or waves that appear on the free surface. Okay. And beyond 1800, it becomes turbulent, right? You can see how turbulence is shown. So eddies are formed and the flow becomes like that, and the movement becomes quite random. And here there is a wavy or rippled flow. Now at what point, at what value of Reynolds number will it become wavy laminar, or it will become turbulent? So generally between 450 and 1800, it is wavy laminar, right? Actually beyond 30 itself, it is like some effect is seen. Okay. But beyond 450, surely it becomes wavy laminar. But there is some disagreement between the value of Reynolds number at which it will become wavy laminar or turbulent. But for our purpose, we may like accept these numbers 30 and 1800 as the point at which the wavy laminar starts and the point at which the turbulence starts. Of course, we are not going into much analysis of the condensation heat transfer phenomena over a vertical plate. Generally, the analysis start with this case, this example, but we are not going into details of that. We'll just have look at the final correlation that you get. Right, if you want to get the thickness of the condensate, then it can be found with the help of this formula. Right, thickness of the film can be found from this formula. This is for this particular case, again with the assumption of laminar flow. This is not talking about the region outside the laminar flow. So Reynolds number has to be less than 30 for using these correlations. And the correlation for H, the heat transfer coefficient. Now this is local value of heat transfer coefficient, but you are generally interested in the whole height. So in that case, H average is equal to 1 upon L. You have to integrate H from x equal to 0 to x equal to L. And it is found that it is 4 by, and or you can show it with this previous equation, that it would be 4 by 3 of the value of H at L. Okay. So whatever H you find, heat transfer coefficient at x equal to L, if you take 4 by 3 of that, then you will get the average heat transfer coefficient. So this means that heat transfer coefficients are higher at value of x less than L, right? Because as the thickness of the film goes on increasing, the value of H is going to decrease. So this correlation may be used for finding the heat transfer coefficient for condensation heat transfer occurring over a vertical flat plate. Okay, that is equation 10.21. Though we are not going to solve any example on condensation. And here you had this HFG, but then if there is significant amount of subcooling occurring, then it is advisable to use HFG star, that is modified HFG. And if it is like vapor is at significantly higher temperature than the saturation temperature, then even the third term may also be added in this HFG. Okay, in terms of Reynolds number, the H for a vertical plate may be found with this correlation shown by 10.24. And then you may talk about the wavy laminar and the turbulent flow regimes. And it is seen that because of this turbulence, there is better mixing and better heat transfer rate. So in case of wavy laminar, it will be higher, right? It is seen to be more by 20% or up to 50% as compared to the laminar flow, and the correlation for the wavy laminar and is shown, right, proposed by different researchers. And finally, the one for turbulent flow, where your Reynolds number is greater than 1800. Okay. Yeah. So this brings us to the end of the discussion on condensation heat transfer phenomena. If it is an inclined plate, then your H on this inclined plane, if the angle is not very low, right? That is your theta with the vertical. If it is less than 60 degrees, if the angle is up to 60, right, you can just use multiply cos theta raised to 1 by 4 to get the h inclined as compared to h vertical. Okay, so you can use the correlations for h vertical and just multiply with cos theta raised to 1 by 4 if this angle with the vertical is less than 60. If it is more than 60, then it is not advisable to use that correlation. Okay. So the heat transfer coefficient for the horizontal tubes is shown where you have like this d here, which is the diameter of the tube. The expression is quite similar to what you had for the vertical plate, except having d in place of the length. And whether horizontal configuration is desirable for higher heat transfer rates or vertical in case of tubes. So it can be shown that if your length is greater than 2.77 d, then the heat transfer coefficient would be higher in horizontal position, right, which will be the case most of the times. So it's advisable to have, if you have that flexibility or freedom, then you should use horizontal cylinder over which the condensation will occur, or it can be a tube. So if you want to put up a tube, it is desirable or it would be preferable to use the horizontal configuration. Okay. Because the reason is obvious that the condensate film will have to travel less before falling down. So the thickness of the film will be smaller as compared to the vertical orientation. And then horizontal tube banks will not go into that because it is a bit advanced topic, though it is very common in the heat exchangers. Will not go into details of that. And the presence of the other gases than the vapor, like if you're talking about steam, then if air is present, okay, then or other gases are present, then they will hinder the heat transfer. Okay. Okay, so this brings us to the end of the discussion on condensation. So we'll now